Okay, in the next couple of videos, we're going to take a look at how we physically graph these by hand. Now, we know how to enter these in on the calculator, and once you get more familiar with these, you'll know this general shape and what it looks like. We should already, but I'm talking about physically plotting point by point ourselves on a polar on the polar plane, so on polar graph paper. All right, so if we're going to graph this, we're going to do this the old-fashioned way, kind of like when you first learned how to graph in the Cartesian coordinate system. That is, you would make a table of points. So we are literally making a table of points, and we'll call this our theta table. Now, traditionally, we need a bunch of thetas, and we are picking for our thetas. The reason you say, well, why are we doing that? Usually we pick for this, the first coordinate. But again, it's solved for r. R is equal to 4 sine of theta. It's going to be much easier to substitute values in for theta, take the sine of them, multiply by 4 to calculate the r than it is to go the reverse direction. If you pick values for r, you're going to have to divide by 4 and do an inverse sine. And hopefully you pick values that are in the domain of inverse sine. You got some problems there. It's much tougher. So we're picking for the thetas almost always. Almost always. All right, so we pick for our theta. Now, it's not like, okay, let's pick some random values. We're going to use values, and we're going to stick with degrees from 0 to 360 when it's appropriate. Now, on the limacons, on the lemniscates, on the roses, for sure, we're going to go 0 to 360. But when you're graphing simple things like circles that are centered at the pole or circles that pass through the pole like this one is, spoiler alert, we're not going to need that many values. And in fact, if we pick from 0 to 360, what's going to happen is you're going to find yourself tracing over the points you've already plotted. So it's already carved out the circle. What I'm saying is it's already carved it out for you. What you're going to be doing is you're just going to be tracing over that same circle. So it's not like you're going to be entering new territory in your graph going out to 360 for the simple ones. So we got to figure out when are we, good enough for the circles. And we'll kind of get a feel for that. So in general, we'll go 0 to 360, and we'll go by, this is kind of like we're picking our theta step here. What should we step by? Well, we could go by 30s. That should give us a pretty accurate picture. Now, this is total overkill, 0 to 360, going by 30s for circles that pass through the pole. Total overkill, but like I said, we'll get a feel for that, and we'll start seeing when we repeat our values. But for limacons, for lemniscates, it will be very, very necessary that we go by these increments. And sometimes we have to go by even smaller increments to get a decent picture here. All right, so 0 to 360. In theory, I would say, okay, let's start with 0 and count by 30s. 30, 60, 90, 120, 150, 180. All I'm doing is counting by 30s here. Then 210, 240, that's right, 270, 300, 330, and right back where we started from. Okay, well, let's see what these values are. Now, I know you say, well, wouldn't you have to go even further than 360? How do you know to stop at 360? Well, we're dealing with trig here. 0 to 360, the period for sine and cosine is 2 pi. So this will encompass everything. If I go past this, I'm just repeating these points. That's all that's going to happen. All right, so we plug in the values. 0 for theta. Sine of 0 is 0. 0 times 4 is 0. So whenever your r is 0, this is kind of a weird point. It doesn't really matter what your theta is. You will always be at the pole. If r is 0, you're at the pole no matter what theta is. So theta could be 175 degrees. Doesn't matter. 0, 175. Plot the pole, go 175 degrees from the pole. It's still the pole. All right, 30 degrees. Sine of 30 is nice. That's a half. Half of 4 is 2. Now for 60, I'm going to have to go to the calculator, because exact values, they're not going to cut it today, because we can do exact values, but we have to plot these on the polar plane. So when I punch this in 4 sine of 60, I get 4 times sine 60. Oh, something I failed to mention last class. See that answer I got? That is not correct. You know why? Because we are in the mode known as radians. I did 4 times the sine of 60 radians. I actually did that on purpose, so I would show you how that mistake is made. Actually, that's not true. I literally screwed up and forgot to tell you, turn your calculator back to degrees. So highlight the degrees, go back, second quit, hit enter again, and hopefully it gives me something better. I believe that's correct. I'm just going to punch it in again just in case. 4 sine of 60, yep. It's about 3.5-ish. I mean, literally, we're plotting this just round to the nearest tenth. This is as good as we're going to get. All right, 90 degrees, that's quadrantal. The sine of 90, excuse me. The sine of 90 is 1. 1 times 4 is 4. All right, now we get to use our reasoning. We are entering quadrant 2. Sine is positive in quadrant 2. 120 degrees has a reference of 60. 60 in quadrant 2, where sine is still positive, so it's going to be the same as 4 sine of 60, really, which is 3.5. All right, 150, quadrant 2, reference of 30, so it'll be the same as the sine of 30. 180, the sine of 180, when you think of the graph of sine, how that's going to work, will be back to 0. So I should say 0 times 4 is back to 0. Okay, 210, now we have just entered quadrant 3. 210 has a reference of 30 in quadrant 3, so here's what I'm thinking in my head. Sine of 210 is the same thing as the sine of 30, really, except you're in quadrant 3 where it's going to be negative. Now, you don't like what I'm doing here? Fine. You got a calculator, you can punch this in directly, but I'm just reasoning through this. The sine of 30 is a half times negative is negative 1/2 times 4 should be negative 2. 240, reference of 60, quadrant 3. This will be negative 3.5. 270 is quadrantal. That'll be negative 1, thinking of the graph of sine. Not negative 1. Negative 1 times 4. How about that? 300 degrees has a reference of 60 in quadrant 4. Sine again is negative, so it'll just be like a 240. 3.5. 330, reference of 30 in quadrant 4. So that'll be a negative 2, same as that guy. And then 360 should put us back to the start and 0. Now again, this is complete and total overkill for a circle that passes through the pole. This will be 100% necessary for your limacons and your lemniscates, but for a circle that passes through the pole, not so much. All right, let's go to the graph. Hopefully you can see those degrees. Yeah, we're good. All right, we're going to simply plot these points as we go. So 0, 0, that one's easy. 2, 30, so second circle, circle radius 2, 30. 3.5, 60, so 1, 2, 3.5, 60. Where are you at? There you are. Just looking at these. 490. Be up there. 3.5, 120. You notice I'm just kind of following along because it's a positive r and a positive theta. At least it is so far. So again, I'm going 3.5, 120, roughly. 2, 150. So where's the second radius? 2, 150. Where are you at? There you are. 2, 150. 0, 180. Again, if your r is 0, you're just going to be right at the pole. Now you notice, let's get rid of this guy. What I have here are 1, 2, 3, 4, 5, 6, 7 dots. And if you think going any further is really going to help our cause, we already knew that this was going to be a circle of diameter 4, and it should be a circle above the pole. That's what sine is. Cosine would be to the right or to the left of the pole. But if it was 4 cosine, it would be to the right. Now, if I keep plotting points, all I'm going to do is plot over the points I've already plotted, because this thing is done. We've already gone in the full circle. All it's going to do is keep repeating these. So if I go further say, okay, let's plot -2, 210. All it's going to do is make my life miserable, because now I have to go -2. 210 is, the screen goes dark, 210 is a counterclockwise direction. So counterclockwise, this is the way of the clock. This is counterclockwise. I got to think, where's 210? Well, there's 180 and 30 more. Why I just plotted over that point that I originally plotted here at 2, 30. If you plot -3.5, 240, -3.5, 240 has a reference of 60. You're just going to be plotting over those same points once again, which pointless. If you want more points to this circle, well, then that's going to require that you pick increments in between. Maybe you try a 45-degree angle. We could definitely do that. And since we're just going to decimals anyway, pick any numbers in between 0 and 30, 30 and 60, 60 and 90, and you will get more accurate, more points to your circle. But this is nothing more than a circle through the pole as predicted. Again, it's not a coincidence that the diameter of that circle is 4. That's the absolute value of our A. It's no coincidence that it's above the pole, as sine always is. Right? We'll try some difficult ones, more difficult ones in the next one.